Hello everyone, and we are now going to begin Open Zemi session number 3 with my master student Fabio Henrique Tanaka, who is going to give us a talk about understanding morphogenesis using neurocellular automata. As in the other talks, during the talk you can ask questions using the YouTube chat. The talk will be more or less 15 minutes, and after that we're gonna have questions from the chat and from the other members of our study group. All right, so now I will turn over to Fabio, and you can begin whenever you want.
Oh, thank you very much, Klaus. So, hello everyone. My name is Fabio Tanaka, and today I will be presenting my research, Understanding Morphogenesis using Cellular Automata. So, let's begin. Here, you can see the outline of what I will be talking today. First of all, let me ask you a question. Have you ever asked yourself how you came to be? I mean, you are a person, a human being with organs and unique characteristics. But in the past, each of us started as a single cell, a zygote that multiplied itself until it formed limbs, organs, and finally, you. But how these cells knew what to become? I mean, how they organized themselves and decide that this one should be a muscle and this one should be a brain cell. This process of developing a body from a single cell or tissue is very complex and is called morphogenesis. And in it, each cell is only able to communicate with other cells that are close to it. In this research, I want to understand this process better. So, to tackle this problem, I'm using a bottom-up approach from the field of artificial life. I am creating a simulation using cellular automatas that can reproduce the process of morphogenesis. And by analyzing this model, I can get more insights about the phenomenon. So, let's start with some definitions. I said that I am using cellular automata, or CAs for short. But what is it? A CA is a grid of cells that have some states. They can be either 1 or 0, black or white, alive or dead. Every frame, each cell looks at the neighboring cells, its neighborhood, and decide what its new state should be, following a simple set of rules. You probably already heard about one of the most famous examples, Conway's Game of Life. This cellular automata has the following rules. If a cell is dead and has 3 neighbors, it becomes alive. Dead is white, alive is black. If a cell is alive and has 2 or 3 neighbors, it stays alive. And finally, if a cell has less than 2 or more than 3 neighbors, it dies of overcrowding. These very simple rules can lead to very complex and emergent behaviors, patterns or properties that are unexpected and appear when the parts interact in a wider whole. As an example, you can see the animation on the right, where these 3 rules are able to do this video that you can see. Conway's Game of Life is a single example of cellular automata. And now that we understand the basics, let's set a more formal definition for it. A cellular automata has 4 components. The first one is the environment itself, a grid with any number of dimensions. The second component are the states that each cell can have, 0 or 1, black or white, A, B, C, or D. They can be anything, and they can be more than 2. The third is a neighborhood function. It basically says what are the neighborhoods of a specific cell. It's a function that receives a cell as an input and outputs the state of its neighbors. The last component is the update rule phi. This is what's the new state of the cell based on its neighbors. The formula on how to calculate the new state A of a cell I at a time t plus 1 is this. You just apply the update rule phi over the neighborhood of the cell I. Let's check another example of a cellular automata. This one is called Elementar Cellular Automata, and it only has one dimension, a row of squares. Its set of states is the same as the game of life, black or white. And the neighborhood of a cell is itself and the ones adjacent to it. Since this neighborhood is made of only 3 cells, the plate rule only has to define what are the next state for each combination of these 3 cells. Here is an example of a possible set of rules. If you see here, for example, if the 3 cells are black, white, and white, the next state for the cell in the middle should be black. On the other hand, if the 3 cells are white, black, and black, the next state for the cell in the middle should be white. If we consider the output white as zeros and output the output black as ones, you can name this set of rules as a binary number. For example, this rule is called 000101110. Here you can see an example of the so-called rule 30. And since a generation of the cellular automata is just a row, we can stack generations below each other and see how the cellular automata develops over time. For example, here is one generation, here is the next one, here is the third one, and so on and so forth. Let's check, for example, here we have white, white, and black. If we check our rules, white, white, and black should result in black. That is what happens here. Now for here, black, black, and black should result in white, as the first rule here suggests. This example that I just showed can keep growing indefinitely if you want. And with only the simple rules, display this complex behavior, this complex pattern that you can see on the screen right now. Now, let me explain what a neurocellular automata is. It is basically the same thing as a normal CA, but instead of the update rule phi, we use a neural network like this image on the right. When it's time to update a cell, for example, like this one in the middle, the network receives the neighborhood as an input and outputs the new state of the cell. The biggest advantage of using a neurocellular automata is that we don't need to choose the rules for the cellular automata by hand, like the other examples I just showed. Meaning that you can try to recreate behaviors that you don't exactly know how to reproduce or how they work. Next, let's talk about some works that are related to my research. Since each cell of the cellular automata has own information about the cells that are close to it, this model can be used to simulate the process of morphogenesis. Here are 2 examples. The first one is called regenerating soft robots through neurocellular automatas. And the researchers used cellular automatas to, as the title suggests, regenerate the robots. They were able to cut these simulated robots in half, and they would grow again. In the second one, the authors used a neurocellular automata to replicate an image. As you can see, if you wait a little, the image starts with a single black point, but a fully trained neurocellular automata develops these points until it becomes an image. In this case, this image of a gecko. These 2 works are an example of a simulation of morphogenesis, because the cells of the cellular automata know where to grow and when to stop, even if there is no central system coordinating every cell. This next work is a little more technical. In it, the researchers evolved a one-dimensional cellular automata that we just talked before to complete computational tasks that require global coordination. They evolved the rules using genetic algorithms. Here is an example of the task of density classification. This is, if the first generation has more black cells than white, when 148 generations have passed, and as you remember as I showed, time passes as we go down, all the cells should be black. And you can see how it processes information and how it evolves until everything is black. It's very interesting that they were able to do this. But what caught my attention was how they analyzed this strategy by examining then the transfer of information in a cellular automata. They borrowed ideas from physical computation, where particles carry information and particle collisions act as processing of this information. To apply this in a cellular automata environment, they had to define two terms. The first one is domain, regions that are computationally homogeneous and are simple to describe. Basically, areas that do not change or keep oscillating, like black and white, black and white, black and white. The second term is they called particles, that are structures that are between these domains. And you can understand them as you can understand them as regular structures that move between these homogeneous areas. Here, you can see the same example I showed before. And this black area here is an example of a domain because it's homogeneous, it doesn't change. And the same thing for this white area here and here. And this area here that may seem gray is actually a checkboard pattern, and is also considered a domain because it keeps oscillating between black and white, black and white, black and white. If we remove these domains to facilitate the visualization, what's left are only the particles. The research named the particles with Greek letters, and you can see how they move over time. And when they collide, something happens. For example, when this particle gamma collides with this particle delta, they form this new particle, and that, after some time, collides with this particle mi, and results in nothing. So with this, they were able to analyze how the computation was done in a cellular automata. With all of this in mind, these are my research goals. As I said before, I want to understand the process of morphogenesis. Specifically, I want to analyze how the transmission of information functions and how it evolves. I propose to use a cellular automata to simulate this behavior, since both processes only have local information for their cells. And after I get a working model, I want to analyze it using the particles framework that I just talked about. I believe that a deeper analysis of the information transferred in this type of simulation of morphogenesis is a field that can still be explored. And since a lot of people asked me before, let me just give you a more practical example of what use a research like this can have. These are nanobots, basically microscopic robots made of organic cells. In the future, we may use cellular automatas to help design these robots that, in turn, can be used for medicine or chemistry. So, what's my current model? I am using a two-dimensional cellular automata, meaning that each generation is a grid, is a square board, where the set of states for each cell is an integer between 0 and 255. So, a grayscale color. The neighborhood of a cell are the cells around it in a fixed radius. For example, if I want radius equals 1, I get all the values inside this area. And if I want radius equals 2, I get all the cells inside this bigger area. For my update rule, I'm using genetic programming trees. I won't go into too much detail about genetic programming, or GPs, but I choose them for two reasons. The first one is that I can create a population of CAs that each one has a different GP tree. Then I can do a process similar to natural selection and select the most fit ones and apply the operations of mutation and crossover. And this is closer of how the phenomenon of morphogenesis emerged in nature. The second reason is that it's a little easier to understand the operations performed by a GP tree when compared to a neural network. And this may make the analysis of the behaviors a little easier. And with this model, I already tried to run some experiments. If you remember the example that I showed earlier, I tried to do something similar with my model, but the results were kind of mixed. Here you can see an example. In the left, it's the image that I tried to recreate using my cellular automata, and on the right, the behavior of my cellular automata. Oh, and this white column here on the right was just because I didn't crop the image very well. And as you can see, it was quite able to replicate this kind of degradé image. So it was good. The second example, I tried to replicate this bad draw Brazilian flag. And it didn't quite replicate it, but it was able to at least generate this rectangular part. The third and fourth example were worse. This one tries to replicate this stickman, but it was only able to produce noise. And this one that tries to replicate a simple X only reproduced half of it, just a diagonal line. I believe that the main reason for this outcome was because the transmission of information on the system, as I said before, is characterized by moving regular structures. And these structures are being evaluated by the fitness function on the genetic programming algorithm. This creates a conflict because to transmit information, the cellular automatas have to create structures that are not part of the target image. But by doing so, it may reduce its own fitness. Since the CA is penalized by trying to transmit information, it is harder for them to complete tasks that require global coordination. So thinking about that, what are my next steps? The first thing I wanted to try is to solve the problem I just showed. For it, I am modifying the cellular automata for the state of each cell to be an array instead of an integer. So this cellular automata will work like a layered image. But only the first layer will be evaluated. So the other layers can be used to transmit information. As you can see in this image, if I want to get the value for the cell in the middle of this neighborhood, I get the value for it for each layer and put it in an array. Then I repeat this process for each cell, getting an array for itself the neighborhood and send them to the genetic programming algorithm. And talking about it, this new model also requires that I change my update function, because now, since the value of each cell is an array, the update function has to return many values, but the traditional trees GPs can only output one value. So I am trying to use Cartesian GPs, a genetic programming technique that uses a graph instead of a tree, and what they mutate are the connections between the nodes or the operations of the nodes. And since the outputs are nodes, I can have more than one. By doing this, I hope to simulate the process of morphogenesis, and I can continue by start analyzing them with the particle framework that I explained before. So, thank you very much for the attention. If you have any questions, I'll be glad to answer them. Thank you.
All right. Thank you very much, Fabio, for the great talk. And now we're going to go to the questions session. First, I will open for some questions from the other students in the study group. And then I will gather if we have any questions from YouTube. We're going to move on from those. Okay, so let's start with questions from the others. So let's start with Ivan. Would you like to ask some questions or some comments regarding Fabio's presentation? Oh, we got something on the chat. Oh, you cannot hear me. Okay, I'm sorry. My Zoom chat was muted. So I just said that I'm gonna ask questions from the students first. So, Ifan, would you like to ask some questions or comments for Fabio's presentation?
Yes, I have two questions. So first question is, I want to ask what kind of images are easy to be replicated by a cellular automata, and what kind of images are hard to be replicated?
So I believe that the simple images are the ones that it's kind of easy to transfer information. If you check here, I think this image is considered easy because each layer has just one color. So you just need to pass information about what's below and what is above. On the other hand, this image has different conditions for each part. For example, this part has to be a darker shade of black, and this one should be a lighter shade of black. This one, it was supposed to be an easy image, but I don't know exactly why it was not able. I think it's because it has different conditions for the right diagonal line and the left diagonal line. And since it has only one layer to pass information, it was only able to produce one of these lines.
I see. So my second question is, you proposed a new model, and
Yes.
I wonder how this model help you in terms of understanding morphogenesis.
So the first thing is that I have to be able to reproduce it to understand it. And since I was not quite able to replicate the images, I don't think I can start a good analysis. And second, since the second layer, or it will have more layers, can act only as ways to transmit information, I can try to analyze them and see how it's possible to transmit information in the process of morphogenesis, almost being like pheromones that are being transmitted, and how this can influence the process. If something is transmitted to say that, oh, you should stop growing.
Okay, I see. Thank you. Thank you for presentation.
All right. Thank you very much, Ivan, for the questions. Next, Jair, would you like to ask some questions or comments for Fabio?
Yes, I have a few questions. How, in your experiment, how do you compare two images? How is it the fitness function?
So the fitness function is basically this. I evolved the cellular automata by a fixed number of generations. In this case, I think it was 40 or 50 generations. Then I get this final image and do a simple L2 loss between what the cell has and what's the target. So if this final color is totally black, that's 255, and here is a little less black, is 250, the difference is 5. And I compute this for every pixel of the image. And I sum them, and this is my final loss.
Oh, I see. You commented about you cannot replicate some images probably because there's the transmission of information that compete with the image itself, right?
Yes.
How could you check that with the experiment if that's really happening?
This is a good question. This is my theory of why this happened. So if it kind of starts to work with the second model, I can analyze if the second and third or so on layers are doing something in the process. I can try to remove them and see if this affects or not the process. If it affects, I will assume that this kind of part that's not being evaluated is only able to transmit data is influencing the final answer. So yeah, if this model starts to work, I will analyze if these other layers are actually doing something.
Oh, I understand. Thank you. Just one more question. You chose to use genetic programming. over neural network.
Yes.
Is there a reason that you didn't choose to use NEAT?
Uh, it was mostly because I think it's kind of easier to understand genetic programming. And I thought about using NEAT after, but when I saw about Cartesian GPs, they don't suffer from bloat and they don't keep growing indefinitely because NEAT can have this. There are some ways to reduce it, but I thought that this would be an advantage.
Nice. Oh, really, the last question now. What building blocks do you use for GP?
So for the moment, I'm trying to use the basic operations, plus, minus, multiplication, division, some constants, 0, 1, half, and for the moment are just this. But maybe after I will try some blocks that are a little more complex, like max and minimum. Still in a process of trial and error.
Nice, thank you.
All right. Thank you very much, Jair. Next, Abe, do you have any questions or comments?
So I think what I want to ask is whether cellular automata can be used in some kind of data compression algorithm, because as we can see, since it extract the rules, maybe it could be used to do a data compression. But the thing is, the rules might be bigger than the data itself if it's too complex. So I want to know your thought about it.
Yes, it's possible to do. And actually, there are people that are studying right this. Because usually the set of rules, let me go back, is much smaller than all the possible combinations. So, for example, if I get this cellular automata, it only has 8 rules. But starting from the single row, it can generate much more data, much more, it can generate more black and white spots that can be traced as information. So yes, it actually can be used, and I don't think what I'm doing is this right now, but it has this capacity because defining the rules usually takes much less space than all the possible combinations of states.
I see. Okay, thank you for that. The second one is a comment. Actually, I was thinking of since you mentioned neurocellular automata, I was thinking about some kind like in neural network there is this architecture called LSTM, which long short-term memory, which is commonly used for period time sequential data. Basically what happened in LSTM is that the output of the previous time stamp, it will be inputted to the neural network as an input. So I was thinking, is it possible to use this approach in the cellular automata too?
So I think what you are saying is basically what a neurocellular automata do, because each cell is being analyzed by the neural network, each state for each time step. For example, this cell in timestamp t pass through the neural network and receive this new state. At time t+1, the same cell passes through the same neural network and gets the other new state. So each new state is passing through the same neural network. Is this what you mean?
Yeah, I guess that's true. Yeah. I didn't really. I thought that the cellular automata input would be different, but now that I think about it, yeah, you're right that the input for cellular automata is basically the previously generated output of the previous timestamp. Yeah, you're right.
Okay, thank you very much for the question.
All right. So, one more, the last student in the group. では、ハクロさん、なんか今日の発表についてコメントとか質問ありますか？
すみません、申し訳ありません。私は遅くなりましたので、前の部分はあんまり聞いてない。すみません。
あ、はい、わかりました。ありがとうございます。Okay, so no questions from Hakuro. So just to finalize, we got two comments, questions from YouTube. So I'm gonna bring them up. The first one was from Daniel Garcia, who asked, like, what does it mean to understand a cellular, because you said, oh, we want to understand morphogenesis with cellular automata. And if we can simplify this thinking, okay, can we understand one cellular automata with another? Like, can we understand a cellular automata by replicating it with this technique? So what exactly do you have in mind when you say understand?
So when I say understand, I want to see how does it, let me think how to phrase this, how it performs the operation. I mean, how does each cell knows when to stop to grow? Is there a signal that's sent to it? Or does it know by their neighbors or something like this? For example, here they analyzed how everything turns, in this case, black by colliding these particles. So they said, oh, if this kind of structure collides with this kind of structures, this form this new type of structure that once collides with this other results in other things. And maybe by knowing this, how these structures work, we can design other cellular automatas with these structures to do something else, and also maybe get some more understanding about the process of morphogenesis.
Okay, I think one thing to think about is that your definition of morphogenesis here, of understanding here, is about like data that is transmitted on the cellular automata level, like information in the cellular automata that will be transmitted. But what you are proposing here are specific rules for evolving the cellular automata. So how do these rules are related with the process of understanding? Couldn't you just use like a cellular automata, like the method that was used using neurocellular automata to evolve and try to find the understanding from there? But I think this would be like a little bit of a deeper, maybe you can think about that a little bit and we can bring that on the future. There's a second question that was also very interesting from Roberto Galotta, which is a nice presentation and interesting topic. I was wondering how much benefit additional extra layers would bring. In particular, how few layers would be necessary to balance results and resource expenses. So you were proposing, okay, let's use some information layers. But when you add more information layers, you need more resources. So how do you balance those?
Oh, this is a very good question. One of the things is that I wanted to understand is how many layers I need. I actually didn't finish modeling this new model, but I really want to explore because I think it's good to know what's the least amount of layers, what's the least amount of resource that you can use to process this information. So just one example, if I am trying to recreate that gecko image, maybe it's one layer for the right leg, one layer for the left leg, one layer for the head. Maybe it's this, or maybe there is just one layer that's able to transmit every information. I think this is an interesting topic for you to analyze once it's ready.
In our next Open Zemi. Bye, everyone.